First, let's take a look at the car itself. The major components of our car are the PCB, Jetson Nano, and camera. The PCB has a few functionalities: a barrel jack that takes a 5-volt input, a boost voltage regulator that converts 5-volt to 8-volt, a microcontroller that generates a PWM signal, and an H-bridge that uses the PWM signal to control the speed and direction. The Jetson Nano is connected to the microcontroller through UART to transfer the speed and angle predicted from the machine learning model we built. It is also connected to a Raspberry Pi camera that captures the view and predicts the lane in real time.
We have a few main functions for software. First, we have the machine learning model. We built a simple CNN model where we use different kernel size and strength to extract different levels of features, like this one over here. This one's a global branch, and this one's a local branch where the kernel size and strength are smaller. And then we concatenate the two results as the final prediction. Let's see how the prediction looks in real-time lane detection. The video on the left shows the real-time input from the camera and the prediction outcome. The video on the right is a self-driving car from the prediction. The angle is first determined by the ratio of left and right block pixels. If there are more left pixels, then it turns left, and vice versa for the other side. The angle is calculated by finding the leftmost or rightmost block pixel on the top row, and it calculates the angle between the center bottom of the image. In each prediction, Jetson sends the calculated angle and speed to the microcontroller, and the sent values are printed out in the terminal.
The main function for the microcontroller is over here. So we first initialize the 3 different PWM channel in 1, 2, and 3 using the built-in ESP IDF API calls over here to configure each of the channels and then set up the duty cycles. Then we initialize our Bluetooth services over here. So this Bluetooth services span across multiple files, so each of them set up a different service for Bluetooth, for advertisement, and GAP and a GAT service. So in the GAT service, we have a function that handles the different Bluetooth event call. So over here, when it receives a signal from Bluetooth, it will update the servo angle as well as the H-bridge PWM signal. Similarly, this UART channel will also do the same. So once it's switched into manual mode, it will read the UART byte and then update the servo angle and PWM signal accordingly.
We also created a website for selecting the mode to operate on, self-driving mode or manual mode. First, let's connect the microcontroller using the connect button. In the control panel, you can press T to toggle the mode of operation.
When you're in the manual control mode, you can hit the arrow keys to control the car.
After we toggle to the self-driving mode, the car detects the lane and drives by itself.